right, let's take a look at today's lesson. It is on derivatives of inverse trig functions and, in general, inverse functions. Okay, derivatives of inverse trig functions and trig, just general inverse functions. Let's focus on the new fun derivatives. Now, I know it looks kind of overwhelming, so we need to just be calm. Okay, I'm going to show you some patterns. There are really only three patterns that you need to know. So let's talk about how that's possible. If you would look at arcsine, now hopefully we recognize that this little -1 here does not mean 1 over sine. They use that on the calculator notation, and it's really fairly disturbing to me that they use that notation because we use it for other things too. But what they mean is inverse, not reciprocal. So this would be the arcsine function. So the derivative of arcsine is 1 over square root of 1 minus x squared. Look at the derivative of arccosine. It is exactly the same, it's just negative. And that pattern that we talked about on the original trig derivatives, where all of the derivatives of the ones that start with a c are negative, that pattern holds here. The arccosine and arccosecant and arccotangent are all negative versions of the other one that they were paired with earlier when we memorized. So we really just have 3 patterns to memorize, knowing that one of them will be negative when it's involved with the one that starts with a C. So it's just something to try to help you. The arctangent and the arccotangent, they're the same, except for the arccotangent is negative. And then the arccosecant and arcsecant are the same, except for the arccosecant is negative. Now, these are really important. They're actually even more important to us when we get to integration. I talk occasionally about integration. Derivatives and integrals are opposite of each other. They're opposite operations of each other, just like multiplication and division are opposite operations. So when we get to integration, we will be integrating something that looks like this, and we would get arccotangent. Okay, so and they love them. I'm just telling you, they love these. You will see them when we're integrating. So that's really important that we get a good grasp on them now and how they're related to which, trig arc function, because you're going to see them all year. You're going to see them. So this over here on the side, to find the inverse trig derivatives by hand, I always have students that are just so interested in why. Why is it this? Why is it that? So I wrote out the whole why. And if you forget one of how to do the derivative of like arcsine, you could actually go through this process and get it by hand. Now, I would really recommend you memorize the derivative so you don't have to go through that process. I'm not going to require you to go through the process. I'm not going to test you on it, but I just thought that it was interesting. Notice it starts out by switching the x and the y. We know that it's in the original, this is my arc function, y equals arcsine x. We know that in the other one, the x and the y would have been just regular sine. The other one, the x and the y were flipped. And so what, how these were created is they basically drew that out on a triangle and worked through just regular cosine derivatives, worked through to get the actual derivative. So that's just a procedure that is kind of fun, like if you don't have anything to do on Friday night, you might want to derive all of the arc functions derivatives by hand. I mean, that would be kind of fun. Yeah, that'd be fun. I mean, just if you're, bored and don't have anything to do, that'd be kind of cool. So that's how you would do it. Again, I'm not going to test you on it. I say that because I have panic when I'm not going to test you on it. I just want you to see how they're created. All right, so that is our information about the derivatives of the inverse trig functions. Now let's practice. All right, let's do a derivative of inverse trig. Okay, our first one is x arctangent root x. Now I'm kind of partial to writing out the word versus using the -1 because I think the -1 is confusing, but we do have to be accustomed to both because you'll see it on the test as -1 and you'll see it both ways. So we just need to be familiar with both. So we look at that, kind of plan our work ahead. Looks like we have multiplication going on there. So we're going to do product rule. And I'm hoping that everybody in here understands that this is not multiplication. The arctangent is not multiplying to root x. This is the argument of arctangent. Okay, that's a common misconception. Just make sure we're okay in here that this is the argument. It's not multiplication, but, and as you recognize, it's going to be a chain rule, right? Because this isn't a regular x, it's the square root of x. So we have to chain everything that's not a formula, not a specific formula. All right, so we're going to have to use fg plus fg, first things first, second things second. So f prime of x equals, so we take the derivative of f, derivative of x is 1, copy paste g, plus, we copy paste f, and then we take the derivative of g. Now I'm going to do a little notation over here. I want to show you how these work. You probably, you've only seen those arc functions for about 5 minutes. You probably haven't had a chance to memorize them yet. So I'll just write over here. So the derivative of arctangent of x is 1 over 1 plus x squared. So let's talk about what happens when we have a chain of one of these complicated formulas. What we're going to do is we're going to take whatever, so in this case, we're going to take this square root of x, and we are going to substitute it into this, think of this as a template. Think of this as our template. We're going to substitute it in here everywhere there's an x. In this case, we only have one x, but if it was arcsecant, we would have a couple of them. So I'm going to take the square root of x, and I'm going to put it right here in place of the x. All right? Then I'm going to have to do what? I'm going to have to multiply by the derivative of the inside. This is the inside function. So I'm going to have to multiply by the derivative of square root of x. Okay, so that's what we're going to do. So let's do that. I'm going to, again, we substitute into this, think of it as a template. So I'm doing the derivative of arctangent root x. That's going to be 1 over 1 plus, I'm going to open up that place where the x is, and I'm going to insert square root of x, or whatever happens to be in the argument, whatever they give to you, that's where you're going to put it. And then, and I'll simplify it in just a moment, but my next step would be to multiply by the derivative of the inside. Okay, so square root of x, again, this is our little work over here. So that is x to the 1/2. So to do derivative of that, we know how to do that, right? So it would be 1/2 x to the negative 1/2. And then our calculus part is done. We just now are going to have to simplify. All right, so let's work on the simplification. So we have f prime of x equals arctangent root x plus, I'm going to simplify this first piece, so it'll be x over 1 plus x times 1 over 2x to the 1/2. Is everybody with me? We're just doing algebra right now. Okay. For here, yeah, square root of x squared, we, this guy right here, well, we could put, yeah, it probably should be absolute value. But, go ahead. Yes. It is, that's right, it is being squared. So this right here guarantees that it's positive. And they usually don't put the absolute value when they're working this through. I mean, it's not that it's not relevant, it's just that they usually don't. They usually just leave it as plain old x. Okay, so in simplifying these two guys right here, I have x to the first and x to the 1/2. So hope we can see what that would leave us, right? X to the 1/2 on top. So that f prime of x is going to be arctangent root x plus x to the 1/2. So I'm just going to change that to be root x over 2 times 1 plus x. You could distribute the 2 if you want to. Be fine. Okay, probably to be perfectly proper, we could just put this absolute value right there just to make sure that we're all good. Okay. How are we? Everybody okay? All right. So let's take a look at this next one. Do I have any arc functions in there? No, it just happens to be just a fun one that we're going to do. It's just no arc functions. It's just a fun one. So let's look at it. So it's pi to something. Pi to x tangent x. Well, that's like, just pi is just a number, right? A number to a variable. So this would be like an exponent, like 2 to the x. That's the derivative rule, the outside derivative rule that we're going to use. Is like so this is our outside function. Pi to the x would be our outside function. Our inside function happens to be a product. Okay, so we're going to use the chain rule and the product rule. Alright, so let's do the chain rule. So derivative of the outside, derivative of pi to something, box or whatever you want to call it, pi to something is pi to the box times ln pi times the derivative of the box. Right? Whatever's in here. We'll just think of this as a box. I mean, they could put anything in there. But my derivative is going to be pi to the box ln pi times the derivative of the box. Right? Okay, so let's do that. So pi to the box ln pi times the derivative of x tangent x. Now that's a product. We're going to have to fall back to this rule right here. So let's see, the derivative of x is 1, copy paste tangent, plus copy paste the x, derivative of tangent is secant squared. And I know you're going to be terribly disappointed to know that we really can't simplify that. I know, darn. It's just going to have to stay like that. Okay. So the next technique we're going to look at is basically all the other inverse functions. How could we take the derivative of them? Now I had the question earlier is, could I use this technique on the trig inverse functions? And you could, but you'd have to go through, you know, that thing I showed you where you're doing it by hand, that whole process. You'd have to go through that. And probably, you know, although it might be fun, we probably don't have time to do that. We just need to memorize the inverse trig derivatives. We just need to memorize them. Okay, we don't really have time to go through and do them by hand. Now this is for inverse functions in general. This is a formula that's pretty helpful. So if we want to, first of all, let's look at the rules. So for differentiability, first of all, it must be differentiable and 1-to-1. Now we're going to look at 1-to-1 and whether it's differentiable. This I think we're pretty familiar with, differentiability, continuous, you know, no corners, no cusp, that kind of thing. 1-to-1 we touch on in pre-cal and maybe algebra 2, but maybe we don't have a really perfect understanding of it. Let's talk about it, what it means to be a 1-to-1 function. So just as an example, if we look at x cubed, we can see that not only is it a function, it passes the vertical line test, it is also a 1-to-1 function because it passes the horizontal line test. Okay, that's what it means to be 1-to-1. Graphically, you would pass the horizontal line test. And I'm going to do that example right now. Yeah, so that would be something that would be considered to be 1-to-1. But we do have functions that aren't 1-to-1. You know, for example, if we have a parabola, say x squared minus 1, that's not 1-to-1. It is a function, so it passes the vertical line test, but it is not 1-to-1 because it does not pass the horizontal line test. But we practiced last year how we could force it to be 1-to-1. Do y'all remember that? We practiced that. We restricted the domain, right? We restricted it and we said, well, this, we're only going to work with it from 0 to infinity, right? We restricted the domain. So it is possible to make a function 1-to-1 with a domain restriction. So just keep that in mind. Even if it's not 1-to-1, we could make it 1-to-1. So that is what we're going to have to do first on this particular problem, is we're going to have to test to see if it is 1-to-1. Now we do not have to fall back on the methods that we used in pre-cal, where we just graphed it and looked at it. We can actually use calculus to determine that. Okay, and so we're going to talk about how would you use calculus to determine if it's 1-to-1. Well, what you would do is you would take the derivative and you would do a sign chart on it. Well, let's talk about what we'd want to see. If the derivative is always positive, what does that mean my function is doing? Always increasing, right? Is that going to be 1 to 1 if it's always increasing? Yes. Okay, what would it be if the derivative was always negative? It would be always decreasing. It would be the opposite, right? And it would also be 1 to 1. So the way that we would determine if it's 1 to 1 is we take the derivative and we set it equal to 0 and do a sign chart. Okay, so let's do that. We're going to determine if it's 1 to 1, and then we're going to find the derivative. That takes me back to this formula just briefly. So the derivative of an inverse formula, I like to think about this part right here. Really the only time that I would use that formula is if I don't have an equation. That's the only time I would use that formula. I would always calculate it by hand. And I'll show you how to do it by hand. Just to me it makes more sense. But if you don't have a formula, and we will work with some of those in time, then you have to fall back on the formula. But let me show you. Let's work it by hand, and then I'll show you how to use the formula. So let's determine first if it's 1 to 1. So we would take the derivative. So f prime of x is 5x to the 4th plus 1. We would want to do the set it equal to 0. So we could set up our sign chart. Okay, so if we solve for x, we're looking for the zeros of the function of our derivative. Are we going to have any zeros of this derivative? Are there any zeros? There are no zeros. Okay, that's imaginary. We can't do that. So on my sign chart, what numbers would I put if I don't have any zeros? I guess any number I want, right? Because there's no zeros. I don't really have to put numbers. I mean, you could, because it really freaked the students out earlier that I didn't put any numbers on it. So just for fun, let's just put a number on it. -1 and 1, wherever. Okay, I'm doing a sign chart. I'm testing the signs. I put any number in here, any number in this derivative that you can think of, any negative number, any positive number, or 0, and what sign am I going to come out with? I'll come out with positive, right? No matter where. It's all positive. So that means that this is always what? Always increasing, always positive, so therefore we are 1 to 1. We are 1 to 1. So this would be yes, we are 1 to 1. Okay, we're talking about derivatives. We're not talking about the main function. Okay? I'm not talking, this is not the main function. This is the derivative of the main function. Okay? So the derivative of x cubed would be s squared, right? 3x squared. Okay? So it is 1 to 1. So therefore, we're going to find the derivative. What I'm going to do is I'm just going to do this by hand, like I think makes sense. We know that this is a y and those are x's. To do the inverse function, we just change x's and y's. Remember that from last year? Or the year before, we just change them. So let's do that. Let me move my work up here so y'all can see. Let's go ahead and just change them. So this is going to be x equals y to the 5th plus y plus 1. Okay, so that is the inverse. That's the inverse. So now I'm going to take the derivative with respect to x. That's what I'm going to do, because that's what we want. The derivative of this we want with respect to x. See how there's x there? We want the derivative with respect to x. So I'm going to do that. So the derivative of x is 1. And then we have 5y to the 4th dy dx plus 1 dy dx. I factor out the dy dx. Get 5y to the 4th plus 1. So dy dx equals 1 over 5y to the 4th plus 1. That's my derivative. Okay, that's how I would just do it by hand. Now, basically, I hope that you can see this formula, how it relates to this. Let's compare these two things right here. Okay? Notice how I have the 1 in the numerator. See, that's the same. Notice how this is dx dy. This means with respect to y, I've got y's in my equation. This has y's in my equation. So these are virtually the same. Okay? Some students ask, well, could I take this and could I turn it upside down? Could I say that this is equal to dy dx? And the answer is, yeah, you could do that, right? Because isn't that what we found up here? We found dy dx. These would be the same. So we're really, this formula will be useful with some abstract applications, okay, which we will get to later. We're not going to work with the abstract applications just yet. Okay? Yes. Yes. Sure. So any other questions on the lesson? On the lesson? Yes. Yeah, there are ways, right. You can do it, that would be using this. Yeah. Yes. Okay. All right.